Okay, for number 6, instead of writing that division problem with the division sign, I'm going to write it as fractions. So it really becomes 5.5 divided by 5 times 10 cubed divided by 10 to the 8th. So if you do 5.5 divided by 5, you get 1.1. And then you keep the 10, but you subtract the exponents. So it ends up being 1.1 times 10 to the negative 5th power. That is scientific notation because 1.1 is a number between 1 and 10, and you're multiplied by a power of 10. For number 10, you have x squared over xy cubed raised to the 3rd. So one thing you could do is you could do x just on the inside. You could keep the x and subtract 2 minus 1 and raise that to the 3rd power. So 2 minus 1, you actually have an x over y cubed raised to the 3rd power, which means the top is cubed and the bottom is cubed. So I would put a 1 on this x and say that's x to the 1 times 3, and this is y to the 3 times 3. So then that gives me x cubed over y to the 9th. Number 11, I'm going to put exponents on everything that doesn't have an exponent. So 2 to the 1st, x to the 1st over y cubed raised to the negative 4th. There's nothing I can simplify inside the parentheses, so every exponent on the inside gets multiplied by the exponent on the outside. So 2 to the 1 times negative 4, x to the 1 times 4, and y cubed, oh, those are negative 4s, times negative 4. So I end up with 2 to the negative 4th, x to the negative 4th, over y to the negative 12th. And anytime you have negative exponents, you have to flip them to the bottom or flip them to the top. So in this case, on the top I'm going to have y to the 12th. On the bottom I'm going to have 2 to the 4th, x to the 4th. So when I simplify this, I have y to the 12th over 16 x to the 4th. Okay, then number 18. When you have like bases, you keep the base and you add the exponents. So I can keep the 3, there's a 1 on that 3, and add 3 plus 1 and multiply that by 2 cubed. So it's 3 to the 4th times 2 cubed. So 3 to the 4th is 81, 2 cubed is 8, and 81 times 8 is 648. For 23, when you have a power of a power, you multiply the exponents. So this becomes 2 to the 3 times 3, which is 2 to the 9th. Number 24, anything to the 0 power is 1. You could have said this is really 3 to the 6 times 0. 6 times 0 is 0, and then 3 to the 0 is going to be 1. And then for 31, when you have power of a power, you multiply the exponents. So this is going to be p to the 4 times 7 and q to the 2 times 7. So 4 times 7 is 28 and 2 times 7 is 14. So p to the 28th, q to the 14th. Okay, for number 15, you have to find the value of each power of 10. So 10 to the negative 9th. Well, I just think of it in scientific notation as 1 times 10 to the negative 9th, which means if that's a negative exponent, I got to get a smaller number. So the decimal is behind the 1, and I would have to move it 9 times to the left. I can move it once in front of the 0, or once in front of the 1, and then I'm going to need 8 more zeros to make 9 spaces. And then my decimal would go right here. So it's going to be a decimal point, then 8 zeros, and then a 1. Number 19, if I'm going to write that as a power of 10, well, 1 million has the decimal at the end. So if I move it all the way back to get a number between 1 and 10, this would be 1 times 10 to the 6th power, But they just wanted it as a power of 10, so you don't need the 1. So just write it as 10 to the 6th. Number 24, if I want to find the value of 0.05 times 10 to the 7th, 7's a positive number, so that means the number's going to get really big, so I got to move the decimal to the right 7 times. I can move it twice to get it behind the 5. Then I would need 5 more zeros to get 7 spots. So this is going to be a 5 followed by 5 more zeros. So that's 500,000. And number 31, if I want to write 235,000 in scientific notation, the decimal starts at the end. Number between 1 and 10 is 2.35, and I move the decimal 1, 2, 3, 4, 5 places. So this is going to be 2.35 times 10, and since that's a number bigger than 1, my 5 had to be positive.